Like, in a world where malachite...
No, it's funny. Keep going.
In a world where malachite green mixes with water in beautiful colors.
Welcome to UConn Spring Semester 2018. This is class Chemical Engineering 4319. We are Group 3, team members Landon Bassett, Tasman Corbett, Connor Marikinak, and Wyatt Pedrick. Major topics covered for this experiment will be chemical reaction kinetics, reactor design using SolidWorks, and computer modeling using COMSOL. The reaction taking place is an alkali bleaching reaction of triphenyl methane mixed with malachite green. This reaction has the following rate equation. Here we relate the Pechet number, which is a good indicator for the environment that the fluid is traveling in, and typically has a characteristic dimension between 500 picometers and a few millimeters, to the Reynolds number, which is the inertial forces divided by the viscous forces. The Reynolds number accounts for characteristics of both the fluid, which density, dynamic viscosity, and the environment in which the fluid is manipulated, such as fluid velocity and characteristic dimension. We had two good indicators for the characteristics of our fluid and also for the environment of our 3D reactor design. For the characteristics of the fluid, we used the Reynolds number, which was indirectly calculated using the Pechet number, which was calculated using the spectrophotometer by Arduino. The first hazardous material we will be using is malachite green. It has acute oral toxicity, serious eye damage, and reproductive toxicity. It is harmful if swallowed, it will cause serious eye damage, and it is suspected of damaging the onboard child. To prevent this, we will be using laboratory coats, gloves, splash-proof goggles. Due to the decomposition products of malachite green being carbon monoxide, carbon dioxide, and nitrogen oxides, we will need to seal this in a tight, closed container.
First run, the concentration starts high and then moves down to steady state in our plug flow. And then we're testing the effect of flow rate.
Excellent.
The extent of reaction will be proportional to the residence time distribution. This can be calculated for non-ideal reactors by using a tracer inert chemical injected into the reactor at time 0 and then measuring the concentration in the effluent stream. The Pechet number is a dimensionless number that shows transport rate. PE equals advective transport rate divided by diffusive transport rate. We expect our Arduino spectrophotometer to absorb less light as the reaction proceeds, therefore our Pechet number should go down. 3 different reactor designs were created in SolidWorks. The first was a base case, the second had many baffles, and the third used medium space.
Everything's gonna go well.
Best practice procedures followed by Group 3 were to first find a calibration curve to normalize the Arduino spectrophotometer to the malachite green. 3 different concentrations were created with varying injection flow rates into the reactors, 10 to the -7 to 10 to the -4 molarity malachite green. Once the malachite green and sodium hydroxide solutions were made, 2 syringes were controlled using a mechanical flow meter. We varied these rates from 1 milliliter per minute to 6 milliliters per minute. Fourth, the syringes were connected to the 2 inlet ports on the reactor. Please pause the video now to continue reading the procedure.
Okay, so now we are pumping, this is DI water in our waste container, and we are pumping it back through the reactor to clear the reactor, get all the bubbles out. It's gonna run into these, we can clean them out, and then refill them. Just wait a second.
Okay.
It'll shift
For Taz's request, we're gonna do the thing where it pops up and over.
Well, the plate will move and fill it with more resin when it's done printing a layer.
Yes. I kind of see now. Ooh, see?
Data analysis.
Well, Taz, why don't you tell me what you're doing?
So we went through and we put all the data in our notebooks separately, and now I am compiling all the data into one lovely spreadsheet to
Excellent.
send to you guys so you can edit the rest of it. And then we can do our data analysis.
That sounds excellent. Don't look at me, though. Act like you're just in the moment.
So I'll be discussing the process behind the design of one of our best reactors in SolidWorks and evaluating it in COMSOL. So here we are in SolidWorks. This was our third design, and the process for creating this was starting with the body. It's 50 millimeters by 100 millimeters. We extruded that up 4 millimeters and extrude cut the design, the inner channel design in that. We extruded 2 millimeters down, so the channel height of our reactor is 2 millimeters high. So the smallest diameter of the channel is 2 millimeters, seen here and here. That would be 2 millimeters. The baffles here are 2 millimeters and 6 millimeters long for scale. This narrowest channel is 6 millimeters long as well. And this is about 45 millimeters long. We decided to go with as many baffles and narrowing and expanding channels to improve mixing. And in terms of our other reactors, it seems to have done that. We also sloped some edges. We noticed that in one reactor there was a lot of bubbles forming in the sharp edges, like here. We'd get bubbles, and we couldn't get those out with a really narrow channel diameter, as well as many of them. So we had one reactor that it was pretty complicated. Maybe had like 40 or 50 of these corners, and it was only 1 millimeter in diameter. And we couldn't get the bubbles out, and it really decreased our volume, and it really probably destroyed the performance of that reactor. So we learned from that, and this is the design we came up with. In order to evaluate this in COMSOL, we need to have a 3D model, a 3D.stl file of the inner channel only. So I'll show you what that looks like. So here's the inner channel geometry only. And then we imported that into COMSOL. So here's our COMSOL. We imported this geometry. We set the entire component material to be water. We have laminar flow in the inlet. The inlets are specified over here. As we can see, these light blue highlighted sections there. And outlet is the end here of this long straight channel. We have, for the physics, transport of diluted species. We specified each inlet differently for each species. Inlet 1, we can see is malachite green, and we had 2 moles per meter cubed, or for NaOH, we had 100 moles per meter cubed, or 0.1 molar. It was a stationary study, and our mesh, we did not create our own mesh. We just selected physics-controlled mesh and extremely coarse. We tried creating our own mesh, and it wouldn't run. This is actually the only way we were able to get this reactor to run, was this combination, physics-controlled mesh and extremely coarse. And in terms of our results, we'll start with the velocity profile. So here's the velocity profile of our reactor, and as we can see, the narrowest sections have the highest velocity, indicated by this light blue color. We would expect that, so that's good. If we look at the concentration profile of malachite green, as we can see in the beginning, there's little mixing and little reaction because there's little mixing. But relatively early on in the reactor, there appears to be a good amount of reaction. And we can see that approaches basically zero malachite green halfway through the reactor. We did not observe this, though, during our experiments. And so we believe that, this isn't 100% accurate. Maybe the reaction rate or the rate constant is wrong. We used the value that we were given and not found in literature, so there might be a better rate constant in literature. If we look at the product concentration gradient, we can see the same thing relatively early on in the reactor. We have a near full extent of reaction. Again, not observed. We observed some malachite green in the outlet, and this would indicate that we have, if we go back here, see it looks like near zero, so that would indicate we wouldn't see any green, because as the reaction proceeds, the color of the effluent goes clear. And so this these are the results of our console.